Now time for some physics. So Hadleigh is talking tonight. There aren't any talks over the mid-semester break. However, they are resuming first week back with Ethan's giving a talk on Rubik's Cubes and the mathematics behind them, which I assume means group theory. Yeah. So, okay, would you like to start your talk now? We'll start all that.
Isn't that nice? I'm really satisfied with that. Like,
Your face is a bit better.
my face is well, that's because I'm saying.
Yeah.
Today. Okay. Well, good evening, everyone. Thank you for coming along on the very last day of term, thank God. Also, the very last day we have Adam, well, the last Friday we have Adam for a long time.
Woohoo!
So obviously it's very sad to be leaving us. And tonight's seminar, or our pre-dinner seminar, is called Spooning Black Holes. And that's because it's basically about the entire universe. And to gain insight into the entire universe, we are going to look at black holes. And the reason I called it Spooning Black Holes is because our predominant visual motif for the evening will be a spoon. It wasn't a Freudian slip on my part. Now, this is kind of, I might just leave that there. It's roughly things that I'm going to talk about. So I'm basically going to tell you about the universe, just like a light introduction to what it is. And then black holes, which you may have heard of before. And then why black holes just mess with absolutely everything and make everything strange. And then why it's cool that black holes make everything strange. That's pretty much what we're going to talk about. And what I think is lovely about this topic is that a lot of this stuff was done in like the 70s and 80s. And I think with this sort of introduction and, I don't know, second year physics at most, you can go and read papers and pretty much understand what's going on. And these are papers which are pretty much questioning, what is stuff, which is reasonably foundational. Okay. So, I've said this a few times before, that really, at least for me, the basic premise of physics is that things exist. And the main object of physics is to write down what things exist. And so, suppose we have a universe which consists of a spoon, and it's a very special spoon because the spoon can either exist like this or like this. Okay? And so, the number of configurations of our universe is 2. And we define this special thing called the number of degrees of freedom of our universe by taking the natural log of the number of different things that can happen, which is natural log of 2. Now, suppose you had more spoons, so you have your universe, and it consists of 3 spoons, and they can be in different configurations. You can have them up and down, and then you have, well, how many configurations can you have with 3 spoons? You've all done like, I don't know, year 10 math.
1!
1, that's right, Adam. A couple, good. So this one can be in 2, this one can be in 2, and this one can be in 2. So there are 2 to the power of 3 different things that our universe can be in. That's the number of configurations. So our degrees of freedom is just 3 times as much. This is good. Why is it good? Because if we were physicists and we were like approaching this universe, there's like the universe over there with like 1 spoon in it, and we were walking over to it to look at it, and the potential amount of information that we could get is like 1 list item thing, right? Because we're physicists, we use MATLAB and whatever. So we'd have spoon 1 is up or down or something. But then we approach this universe, and there are 3 times as many things to know. You have to know about spoon 1, 2, and 3. And so it's good that our number of degrees of freedom here is 3 times as much, because what this is effectively telling us is how much information there is in our universe, or how many, how much stuff is there for an enterprising young physicist to go and find out about. But this is not really very useful to us, because our universe does not consist of 3 spoons. So, in order to apply it to our universe, we are going to do a crash course in quantum field theory. So, quantum field theory, basically, all quantum field theory is, for our purposes, is this framework in which we describe everything, pretty much, apart from gravity. So, all the little particle-y things going around, we describe them using a field, and everyone remembers what a field is. Maybe.
You play like soccer and stuff.
Yes. Okay, sure. What else is a field in mathematics?
Can I play cricket?
Are you saying that mathematicians prefer cricket? No. You're probably right, but I don't know. Look at me. I know nothing about sport. Now, a field in mathematics, the only field I've ever played in, or on, is something where you just assign something to every point. So you just kind of have a thing. I can't write, sorry, but like that's everywhere. There's something at every point in space. Okay, and so the particular type of quantum field theory that we're going to be looking at is something called spoon theory. And spoon theory postulates that the universe consists of infinitesimally small spoons distributed throughout space. We have spoons, and some of them are up, and some of them down. My writing is just getting worse and worse. I've got some. Now, how many different configurations can our spoon field be in? Yeah, here's the problem, right? It's a field, so we've assigned a spoon to every point in space. That means there are infinitely many spoons. That means there are 2 to the power of infinity many different. Mathematician is like gasping for air over there when I did that. There is a correct notation for writing this, by the way.
That's legit.
Adam's really getting into this one, making the most of his last seminar. So the point is there are like lots and lots, and I've just used an equal sign. There are lots and lots of spoons, so many that there are infinity of them. Okay, so this is a problem, and the way we resolve it, we don't really know what we're doing at this point, to be honest. We kind of just, the LHC takes us so far, only so much. But what we do is we say it doesn't make sense for 2 infinitesimally small spoons to be less than the Planck length close to each other. And the Planck length is a really small length, 10, I think, to the negative 35, it's 30-something meters. 34? I don't know. Doesn't matter. Point is, it's incredibly small. And it's around there as well. It's like, it could be the Planck length times 10 or divided by 10 or 100 or something. But what we say is it makes no sense to have 2 spoons closer than the Planck length together. And when we get to black holes, we'll find out why. But just assume that it makes no sense. And that means that our spoon field, which, a spoon at every point in space, is really not going to be infinitely packed. You're not going to have spoons between spoons between spoons between spoons. You're going to have, say, a grid of spoons. And the grid of spoons is going to be a Planck length apart. And so that means that each spoon takes up a volume in space of the Planck length cubed. So, if our universe had a volume bowl, then the number of spoons in that volume is the volume divided by the Planck length cubed. That's like the most complicated maths we've had so far. And the way I'm going to write that is V. So I'm going to call that number V. And V is just going to be the number of spoons, right, in that volume. for this case. Now, the way I want the physicists to think about this is the volume but measured in Planck units, right? So this is the volume measured in Planck thing. Because measuring volumes in meters doesn't make sense, because a meter is like really big. So that's our volume V, and now I ask you the question, how many degrees of freedom, or we can also call this the entropy soon, how many degrees of freedom does our universe have? Does the spoon field in the universe have? Good. N is V log 2. There are 2 to the power of V different ways that field could be configured. Lovely. So that's quantum field theory. Good. The other thing that we're going to do first is remind ourselves about something called thermodynamics, which, well, I mean, that relates to gases, right? So gases are they're a bit further apart than the Planck length. Like something like 10 trillion, quadrillion times further apart than the Planck length. But there's still a whole lot of particles, and they could each be in different states. And back then we defined entropy of a gas, and effectively the entropy of the gas is just the same here. Do you remember in statistical mechanics we had entropy is equal to natural log of omega? It's still the same, right? So entropy is just telling you the number of degrees of freedom. The way we used to think about it in thermodynamics was entropy is kind of how much we don't know. Because we know the pressure, we know the temperature, but we don't know the velocities and blah, blah, blah of every little particle. But entropy, defined this way, as like the number of degrees of freedom, is more general than that. It's more how much information is there to know, and we can apply that to a computer, or to a universe, or to a box of hydrogen gas. Now, in thermodynamics, sorry, that sounded really loud in my ears. In thermodynamics, we have 2 important laws. The first law relates to the flow of energy around the place. I can't remember which number it is, but it says something like a change in energy is equal to TdS, which for a gas is heat added, minus PdW, something like that, or dV. No, that's dW. See? Letters. Something like that, which for our purposes is going to mean that the temperature of a gas is defined as the rate of change of the energy of the gas divided by the entropy. And because entropy is defined more generally, we can apply this more generally, and we can say that things have temperature, and then we can check to see whether that made any sense to give a computer or a universe a temperature. You can see that physicists are very rigorous in our thinking on these subjects. Now, the second law is that, what happens to entropy in the universe? What's been going on for like 13.6 or 4 or 7 or however many billion years? It's been increasing. So that means that ds is always bigger than 0. Good, so we've done thermodynamics. It could be equal to, because you could have like one point in time where the universe looked like this, and then you could have a quantum interaction happening over here, but then you could take a point in time in between where the universe still looks like this, and then entropy would be the same because nothing happened yet. If you had a universe that was trackable enough. Of course, what the problem is where in the universe. So in order to know that it's still in the same state here, we have to do a quantum interaction, which has just broken our rule. In other words, it really stinks that we have to live in our own universe. Like, it would be better if our own universe was over there, and we could look at it, and then go home, and then, get it out the next morning. Good. So, now we're going to introduce black holes, which means we're up to talking about the second thing on my list of things to talk about. Now, basically, what happens, which is a really cool thing, I think, is, and this isn't told unto us by quantum field theory or thermodynamics, but it's told unto us by Einstein and the equivalence principle and whatnot, that if you have some mass, m, and you squeeze it within a sphere of radius smaller than 2m, then you get a thing which is so compact that it doesn't let anything out of the thing, and including light. So the curvature of space around the thing is so much, the gravitational strength is so much that any piece of light coming along is like, ooh, yay, and goes down the hole. And this happens whatever, right? Like, you could take this air, and then you could squish it really, really small, and you could get a black hole. It would probably evaporate very fast, but we don't know that yet. But yeah, that's all there really is to it. But this is an important point, right? So remember I talked about the Planck thing. So you got a Planck thing there. And we want to think about, does the Planck length make any sense? So we want to find the smallest thing in the universe that's like the lightest. Or just choose a small light thing. And that's actually a pun as well. Hint, hint. Choose a photon, okay. So we have photons here, lots of them. They're not particularly high energy, and I take one of them. And then I run over here, and I squeeze it inside the Planck length. So I take my photon and I squish it, inside the Planck length. What do I have to do to fit a photon inside the Planck length?
Jam it in real tight.
Good.
That's what she said.
Don't you lose the notion of its energy?
Sorry?
Don't you lose any certainty about its energy as well?
Yeah, well, I mean, yeah, quantum mechanics happens too, but, which is another problem in the Planck length, right, quantum mechanics.
Yeah.
But one of the cool problems introduced by this is that you have to increase the energy a lot, right? Because you remember that energy equals h over lambda or something. Now, you put a c there too. In order to get lambda really small, you have to make energy really big. And you actually have to make the energy so big, and if we just set c to 1, then energy is equal to mass. So I'll just write that. So we have to make energy really, really big, the photon, and it turns out that the energy that we have to make it is such that there is so much stuff inside this scale that it's too small, right? And a black hole forms out of a photon. So the problem with the Planck length is that if you squish anything in the universe, probably that we know about, smaller than the Planck length, that makes this too big and this too small, so that this is bigger than this, and whenever that happens, we get a black hole. And so what's that telling us? I mean, obviously, we don't know that we get a black hole, because we've never done that experiment. You can't do that experiment yet, because we're not like from Atlantis or something. But that doesn't matter. The point is that this is where physics breaks, because we have quantum mechanics going on, and you also, if you want, can do the exercise, I leave it to you, to show that crazy things happen to your uncertainties in position and momentum at that length. Okay? But this is telling us that like gravity and just quantum mechanics and stuff, no sense. This does not make sense anymore. And this is why. What else do we know about black holes? Oh, okay, so what is the area of, so black holes, let's pretend that they're roughly spherical, if we can say that they have a shape. And then we can say that the area of the thing is this, which is 416 pi e squared or m squared. So the area of the black hole depends on the amount of stuff inside of it. But when we defined what happens when we created a black hole, we said that stuff doesn't come out of it. That's what was so special and amazing. So that means that this thing is always going up. So that means that the area always increases. Which was a paper published in 1971. It took them, that long to realize. So you can go read that. It's by Hawking, and it's quite short. And yeah, as I say, a lot of this maths is very accessible and reasonably interesting. Now, the next thing that happens, is that you go away and you think about black holes for a very long time, and you come up with something called the no-care theorem, which kind of relates to something that the geometers and the mathematicians know about, where you have surfaces where you always have cares sticking up or whatever.
Hairy ball theorem.
Sorry?
The hairy ball theorem?
Yeah. In this case, the no-care theorem, when you apply it to the geometry of black holes, tells you that every black hole can be fully described by its angular momentum, its mass, and its charge. Which is the point at which we go, really? You've got this thing which has like, I don't know, a couple of billions, billions. Say billions and billions of kilograms of stuff in it. It's all been squished, and you're saying that this is all you need. Like, how is it spinning, how much stuff is there, and does it have any charge? And somehow they proved it, don't ask me how, but it raises an immediate problem, right? Because this is the kind of thing we associate with a single particle, or in our previous language, a single spoon, right? So, a single particle, you can describe it fully with this. And you're saying now that the total amount of information that a black hole has is just that. Problem. Why? Because if I put my black hole over here, and then I put a little spoon, the spoon has positive entropy. In other words, there's quite a lot to know about this spoon, because there are quite a few things inside it. Quite a lot of, infinitesimally small spoons in our spoon field. We throw it into the black hole. What happens? All that information of stuff that an enterprising physicist could go and find out about the spoon is gone. Now there are only 3 things to find out. So he has to go home disappointed. So what does this mean? This means that entropy is disappearing. It's like, where is my S? And it's a reasonably big problem. And so, in order to resolve the problem, you can imagine what we might have to do. Effectively, we have to do thermodynamics on black holes. And does Hawking have a Nobel Prize?
No.
Okay. This is the thing that made Hawking kind of cool, I think, amongst other things. But one of his most popularized notions is that black holes have... What did he show black holes have? It's like one of our little bedtime stories. Like, you have your baby physicist and you're like, in 1972, Hawking got up and wrote a paper in which he showed that black holes have temperature. And do you remember why? Like, black holes don't let anything out. Things that have temperature let stuff out. That's why they have temperature in it. Well, that's kind of all wrapped up in what it means to have a temperature. So, why on earth can a black hole have a temperature?
Because it has energy and it changes when spoons rank.
Well, the thing is that it didn't have entropy because it's just described by the no-care theorem, and we're like, oh my god, black holes have no entropy, which is what they believed in 1970. That was foreshadowing, as if I might be about to tell you that they do have entropy, but ignore that. So, T, how can it have a temperature, how can it radiate is the question. And effectively what has to happen, and we've only calculated this semi-right so far. What do I mean by that? I mean we only know this insofar as we know quantum mechanics and we know black holes, and as we've already shown with like squeezing photons, we don't really know what happens when quantum mechanics and black holes get together for Friday drinks. So you have this black hole thing and you have some threshold, and what happens is around here you have a whole lot of quantum events happening and you have virtual particle pairs appearing, and because it's so close and the curvature is so massive, you can have one particle fall in and the other one go away. If you do that calculation like Hawking, then you find that the intensity, the spectral intensity, whatever they call it, like the amount of stuff and the amount of wavelength of things, how it depends on wavelength, you get a thing like that. In other words, you get a black body thing, right? So what Hawking showed is that black holes emit light, and they emit light the same way that other things that we warm up heat emit light, and the temperature of the way that black holes emit light is consistent with an object that has a temperature of 1/8 pi m. There are, I don't know, I think there's a G in there, and there's a K in there, and there's probably a C in there, but you know, those are just constants. The important point is that T is 1/m. Or energy, right? What is weird about that? Like, if you had a thing and you added energy to it, would temperature go down? Probably not, right? That's one of the things that you do in Phys 101, and then your helpful tutor comes along and says you're wrong, because that does not happen. Unless they were doing it about black holes, because that does happen. Which incidentally means that the temperature gets really high when the black hole is really small, which means that when you have a black hole the size of a photon, it's going to radiate lots really quickly and it's going to all put away. But if you have a really big one, it's going to be really slow to whittle away. Which is kind of, it's my favorite thing about black holes. I don't know what yours is, but that's kind of my favorite. Okay. So, the next thing we want to do is ask whether black holes have an entropy. And we can, for that, we can remember, why would we expect them to have an entropy, by the way?
Just because everything else does?
Well, everything with temperature does, right? If you had, if I show you my spoon, which has been cooled to absolute zero, and I get you to have a look at it, and you're like, yes, this has no entropy. Thank you, sir. And take back the spoon. But as long as it has some temperature, it's going to have some entropy, right? It's not just going to be sitting there, there are going to be things to find out about it. So, consider that relation up there. I'm just going to write it down, and we can write it down like dm, say, I'll say dE equals TdS in this case. Now, over here, we can work out how area changes with energy, right? We can say dA with respect to energy. So, how fast does A increase with respect to energy? 2 times 16, which is 4 times 8 pi E. Good. This rearranged, I'm going to put the dE on one side and everything else on the other side, gives you 1 over 4 times 1 over 8 pi E times dA equals dE. Why is that cool? Because we have an expression for a little bit of energy up there in terms of our thermodynamic quantity T and S. And down here we have it in terms of a quarter of this times this. What's special about this bit? It's the temperature. Oh my goodness, that's so exciting. So we replace that with T, and now what do we know? So we equate these two things, and we get a quarter T dA equals T ds, which means that a quarter dA equals ds, which means that S, our entropy, the amount of information there is to know about the black hole, the number of degrees of freedom of the black hole, is equal to the surface area of the black hole divided by 4. Lovely. So, all we have to do to resolve the problem that our entropy from our spoon, our information, our job for the physicist to do was going away when we threw it into a black hole, all we have to do is modify this. And we have to say that the entropy that we normally associate with things, so like when stuff has temperature, it's entropy, that entropy plus the black hole entropy, that's going to be our new thing. It's going to be our new total energy. So, this is like the generalized thermodynamic law of the universe, is that S total is like this thing, which we're not really sure if this is the same as the old entropy, but, you know, so we'll call it S black hole, plus S from like matter and stuff. That's the total entropy, and we're saying that this thing always increases. So we've pretty much resolved the hairy problem by giving black holes entropy. And that is the major change. Like pre-1976, black holes were physical objects that caused human physicists an infinite amount of confusion. And then post-1976, they weren't so confusing anymore because we knew that, you know, that the information wasn't just disappearing. Of course, black holes don't let anything out, so what this means is still something of a mystery. This is a problem, though, for physics. And to see why, what we're going to have to do is create a black hole. So suppose we have 3 spoons. So our universe now consists of 4 spoons. So we're kind of building up a bit. So we have 3 spoons, and it's inside a sphere of radius r. And suppose that these 3 spoons alone, like are really, really heavy spoons, and that means that the mass is almost that critical mass, right? To, you know, r over 2. So the mass is almost r over 2. Not quite, though. And then we've also got this spoon over here. What we're going to do is give this spoon a gentle push, or something, and it's going to float inside the thing, and then it's going to hit here, and they're going to form a black hole, and then spoons will be gone. And the question that we want to ask is, what happens to the entropy in this situation? So I've got those 3, which are in my special shell, and then I've got this one that I'm adding. So, what is the total entropy of our 4-spoon universe before we create a black hole? Oh, no. These spoons are now like Death Star-sized spoons containing lots and lots and lots of metal and gas and stuff. Sorry to kind of confuse things. And yeah, who knows how much entropy. They're all, you know, we bought our Death Star spoons from different manufacturers, so they all have, you know, different masses and things. So I'm going to call these spoons S matter or something. So we'll call that S matter. And then we're going to add to that the entropy from the other spoon, right? So that's going to be like our S. No, these are not fundamental particles of the universe. These are Death Star-sized spoons.
All 4 of them?
All 4 of them. Except this one is kind of smaller because with these 3 spoons we almost had enough to make a black hole, but not quite. So this is like S extra or something. And what's our final entropy?
Is black hole.
Yeah, which is? Yeah, good. So we've got a quarter of area and that, and we've generalized the notion of entropy in the universe, of information in the universe, so that this has to be bigger than this. So we know that S matter plus S external is less than or equal to that. As far as it makes no sense to talk about negative entropy. So this is a positive number, the entropy of the extra spoon. So if that holds, then this must hold. And so basically, and this is a bound that was derived, I don't know, 10 years or something, maybe more. No, it was derived about when I was being born by Susskind and other people. That the entropy of matter that's kind of spherically distributed within a shell of surface area A, this gives you an upper bound, right, on the entropy of the matter in that shell. Now, does that conflict with something that perhaps we may have been talking about earlier? So this is basically saying that in the universe, entropy is capped by the surface area of the region around it, roughly speaking. What does that conflict with? No, well,
probably approach that limit.
yeah. Well, incidentally, this limit is perfectly satisfied if your matter is a black hole, obviously.
Is this still capped for this matter? Or?
Just like anywhere in the universe. The spoons could have been anything, right? I just used them because I've got a lot of spoons and I needed something to demonstrate it. So we've just got this region of the universe, and we're saying that by our derivation, the entropy is capped off by the surface area of this region. But earlier, we were talking about it, and we were talking about the way we describe the universe, and we said that the entropy or the degrees of freedom or whatever go something like the volume, measured in Planck's units, but go like the volume. And so you can imagine you just make the sphere big enough, and this entropy is now breaking our bound, which means that there's not this much information. There's not as much information as we thought there was when we were doing, spoon theory and, postulating the fundamental nature of particles and whatnot. So, what do we have to say to this? Either we can say that this entropy this bound is wrong, and we were going to talk about the Bekenstein bound, but, time and things. So, assuming that this holds, then we have to say that this is wrong. We have to say that the amount of information in the universe is not that dense, that there's less information. And that means that we have to say that a region in space bounded by a sphere of surface area A has to be fully described by A over 4. So we could have measured this in Planck units, right? And then A over 4 would have given us the number of infinitesimally small spoons, right, on the surface, right? So it has to be described by this much information, which is significantly smaller than the amount than V, the amount of information we were considering previously. Why is this bad? Well, it's bad because quantum field theory fails, and quantum field theory is like one of our best things. But it's good because we know why it fails. We know that gravity is messing stuff up for us, and this should hopefully, with any luck, give us a clue as to what happens when you squish a photon smaller than the Planck thing. As hopefully, well, I hope we will one day do, using some big machine in space or something. Now, I should note, if you were going to read on this bound does not hold in general. So in general, they thought, oh, maybe any region of space with a surface area A, could look like a banana or something. Then that would have this cap on how much information can be inside it. Turns out that that's completely and utterly wrong, but you can actually do something to get around that and do a nice general mathematical formulation. So the point is, the problem is still there, and it has been around now in its fully formulated and beautifully compact form for about, I don't know, 8 to 10 years. So why should we be interested in this? Well, progress in physics, at least, has been marked by massive changes in either the way we think about things, so the way we write down what we know, or by spotting new particles. You know, when Newton, everyone went from thinking about the way the moon must move and the way that cricket ball must move as differently. But then he says, well, maybe we can think about them as in the same description. And then in relativity, we also rechanged how we thought about the description. And then we had gauge principles for doing quantum field theory, which changed how we think about the description. And each of these is about incorporating a new principle or a new pattern or something that doesn't make sense into the way we describe the universe. We have a new pattern. The new pattern is that the amount of energy, the amount of information in a space is really very small. And so we should use this to think more carefully about how we describe the universe, because in effect this is telling us that we're doing it wrong. And I think, just to talk more about why this is weird, right? It kind of violates the idea that each point in space is unto its own, right? That because in physics what we do is we write down local orders. So we go, this point in space can be completely described by that point and just the stuff that's right next to it. I don't need to know about the painting at the back of the room in order to describe, a molecule of hydrogen or something that I'm looking at here. But the holographic principle is telling us, if you put a sphere around this room, including the hydrogen molecule and that painting, there's not enough, the list for us to write down the stuff that's in this room is not long enough for me to write down the hydrogen molecule and write down the painting and give them each their own item in the list. And so that means that the hydrogen molecule and the painting and stuff are all coming out of a much smaller set of information, which incidentally is how holograms work, and incidentally is why this is called the holographic principle. Because in holograms, you have a 2D thing, you put light through it, and you end up with the two beams of light coming together and creating something that's actually three-dimensional, not just surface three-dimensional, but like if you cut layers through the thing that you produce holographically, you have 3 dimensions of information. But it's all encoded into one sheet. Very, very cool thing to do. And it seems that that's what's happening in this room right now, and in black holes and everywhere. That the information that physicists go and write down is all coming out of a much smaller little picture. The problem with this is that we don't know what the picture is. We know that there's a lot less information, but we don't know what the information looks like. We don't know the language. And so this means that this is, really frustrating for physicists, because they have to go to bed each night knowing that, there is some way to describe the universe out there using much, neater letters or whatever, a smaller alphabet, say, and we don't know it yet. And as well as that, the universe is perhaps more interconnected than we thought it was, because you can't just talk about things on their own. Presumably in the holographic language, you write down the stuff, and like one line, say, if you were writing down a list in the holographic list of information, one line would affect not just this point, but also that point, and a little bit of that point, a little bit of this point. So you can't just talk about this point, because when you talk about this point, you're talking about all the other points, all at once. You see why this is really like paradigm breaking sort of stuff. We kind of have to throw away the way we like to think about the universe. So what have we talked about? We've talked about how physics is about looking at information and how information is distributed in the universe and how much information there is we can describe by looking at, the number of different things there is. And currently, we think, in our current theories, information increases linearly with volume. You double the volume, you double the amount of information. Now, if you add gravity, it breaks. And this gives us a clue as to how to go forward with 21st century physics, or if we're unlucky, 22nd century. And I hope we're not more unlucky than that, because that would really suck. Yes. If you want to read more, I would suggest you type in Bekenstein and narrow your criteria to 1970 to 1980. And the papers are beautiful. Have a good evening.
So, any questions? Question.
Earlier we were talking about the temperature of black holes and these virtual particle pairs forming along the event horizon, and one of them being thrown off and one of them falling in. How is that the process which leads to a black hole evaporating? Nothing is actually...
It loses gravitational energy somehow. Because, like, when things move away from, when you, like, pull things away from the black hole, you're pulling on the black hole.
Yeah,
right?
that makes sense.
So, which kind of, you'd think means you're doing work on the black hole, and you're kind of doing work on the space-time around the black hole, and by doing work on the space-time around the black hole, somehow that means that the black hole loses energy.
Yeah.
So just the process of something moving away from the black hole is enough to lose its energy. To be honest, for instance, the Bekenstein bound is based on when you lower something into the black hole gets to do work on it, which tells you about how much mass, how much energy the black hole can lose and gain. And that's what produces the bound, which is why it's a very interesting derivation. It's very simple, very short. But yes, it's actually, I don't understand how that happens, because I don't understand how to write down like space-time around black holes when things are moving in and out of them. But as far as I know, that's why. And of course, the funny thing about this is we talk as if we know about how black holes behave. We've not really seen any. We just we can infer their presence, and then we can pretend that we know how to write down what they do. I don't mean that as an attack on physics, just I think it's kind of funny.
So is one of the main problems essentially with this is that it's all got some, this is what I gathered from it, so correct me if I'm wrong, which I probably am, is that it's all got something to do with gravity, and essentially we don't know enough about, like, I guess the fundamentals of gravity or something like that, or because...
I mean, gravity is a theory which came out of the equivalence principle. And quantum field theory is a theory that came out of the gauge principle. They're both really good, because they both came out of us going, this happens. The masses, things move through gravitational fields regardless of their masses, and you can describe symmetries of electrons and whatnot. Electron field. So they both came out of us going, gravity, there's the thing that happens. Fields, there's the thing that happens. Cool principle that makes it easy to write down what happens. Theory. We've never played with the Planck leg and looked at things squishing around there. So we've never looked at something and gone, here's a cool principle, here's a cool theory. So, in effect, this is one of the first truly astonishing things that we can know about that actually is kind of the equivalent of playing around at the Planck leg and seeing what happens. This is like, so yeah, you're right, we don't know. We just haven't looked at those phenomena. We haven't looked at the phenomena where fieldy things happen, gaugy things happen, and curvy space-time things happen. So, because of that, we need more things like this. We probably need more than just entropy bounds. We need, like, just totally new things. And this is the first totally new thing we found. And of course, as far as fundamental theories go, you could look at things like loop quantum gravity and, dare I mention it, string theory, or spoon theory. And that is one of the key reasons why string theorists are getting excited, because you have ADS-CFT, which is highly motivated by the fact that in that theory there is an entropy bound, there's a bound on the amount of information in the universe that looks remarkably like that one. So, yeah, people are looking. But as I say, we don't even, we just assume we know what we're talking about. Because, you know, the engineers haven't caught up with how far we're thinking, and they haven't built us ships to go look at this.
It's almost like you got a theory explaining the theory, as opposed to kind of like...
That's
yeah.
I mean, theories don't explain, they just describe better.
Yeah.
And that's always been the case. Like, our first theory is like, things go down. And it's like, good. That describes things reasonably well until you throw a thing really fast that way, and you notice that it comes back and hits you on the head. So then you go, oh, maybe things don't always go down. And then you think, well, actually, we've got this more general thing. Like, when I give this thing a push, it moves. And maybe there's an invisible push happening. On you go. You have something which takes into account two theories. First theory, things go down. Second theory, if you throw things really fast that way, it hits you on the head. So now your theory is better, and it makes predictions. It makes the prediction that, you know, planets be spherical and things move around in circles, well, ellipses and whatnot. So it leads to new phenomena, and that gets boring after like 50 years, or 100, or 200, or whatever, because your theory is just explaining everything. But then you start to find something that hits you in the head that is not included in the theory, and you make a new one. But all it's doing is you're just describing things. And it turns out that when you take into account new observations, and you describe them together, it usually leads you to think about things you haven't thought about yet. Which is why physics is a productive enterprise, and not just an enterprise in listing the quantum states of the micro nanospoons in this spoon.
Does anyone have any idea how squished things are in black holes?
Well, in the GR description, infinitely squished. But yeah, that's the point. The point is that from this and other things, we know that things can't be infinitely squished. So a black hole is something that we can't describe. We can't say it's squished this much inside a black hole, because information doesn't really make sense anymore the way we think about things being squished. You can't make a measurement of the squishiness of a black hole, right? And the amount of information that you'd expect to be inside the black hole isn't there. You only have like a surface of the black hole. So black holes are these, like we could take this room and we could collapse it into a black hole, and then every single thing that's happening in this room would now appear on the surface of the black hole. And so it no longer makes sense to talk about the squishiness, because inside the black hole, it might not be that there are 3 dimensions with people breathing and sitting around. Probably isn't. You know, it might rather be that there is some kind of, maybe inside the black hole you have a holographic plate instead of the projection of the hologram, to use that analogy. Don't overuse that analogy. Don't let kind of voodoo-ish thinking you know, let us run around and say, ooh, we're a hologram. That's not what's interesting. What's interesting is that information doesn't make sense. Sorry? What about the people inside the black hole? Yeah, what happened? The black hole people. Sorry, it's been a long 3 days.
Hadleigh, how does the Hadleigh fund? So,
it's like G over H bar C or something.
So do we get that from quantum field theory or general relativity, or?
Well, you can get it from GR, or you can get it from just the uncertainty principle. So you can go ahead and work out what length the uncertainty principle breaks down. Like uncertainties go to infinity or something. working out at what length does everything be a black hole. and that calculation would do that. And you can see that it takes into account everything, right? Because energy is H. C? And so we've got C and H. And then we have the Schwarzschild radius, which is 2m, g, stuff. All the other stuff I say equals 1. But the important point is you got H, you got C, and you got G. And if you do the calculation, you end up with a relationship between those if you define the Planck length as we did. It's defined in terms of the fundamental constants. In fact, all the Planck units, so the Planck units are what you measure things in if you set C and H and K and G all to 1. And so if you measure things in Planck units, you don't have to remember as much letters. Excuse the grammar, it'll get better after.
Do you mean K as in the curvature?
No, I meant K there as in Boltzmann's constant.
Oh, right.
KB. And I mean, one of the things I omitted in here, like if you actually want to do this properly, T isn't 1 over 8 pi m. That's just what T is for a Schwarzschild black hole. But more generally, you'll have black holes which have different gravitational intensities, which is the kappa that you'll see floating around a lot. And the temperature depends on that. Like if it's more gravitationally intense, then I don't know, higher or lower temperature. Lower, probably. Just because it has like a negative, what do we call that in like pre-physics? In level 100 physics, what's how much energy changes when you change the temperature? What's that called? Specific heat. Is it?
Yeah.
Yeah, that. It has a negative specific heat. In other words, it decreases with energy instead of increasing. Phonons? What about phonons? What do you think a phonon is? Well, basically, just fun fact, phonons, like in quantum field theory, we get really good at describing how fields like vibrate and wiggle in such a way that you have like each wiggle in the field, each way that the field wiggles corresponds to a particle. We worked really hard on that description. Well, I didn't. They worked really hard on that description in the 60s. I'm not that old. And it was really good and successful, and the maths is cool, except it breaks down and we need proofs and things. Half these things, by the way, Benedict, are not proved mathematically. Well, some of the theorems, so you can do that. The thing about phonons is that description that we have is really good when you have big things as well. So suppose you've got a mattress and you vibrate the mattress. There are going to be different ways the mattress vibrates, and it's really cool to assign each way it vibrates with a phonon, as if the phonon was like the particles that we describe in field theory. So phonons are not like necessarily quantum. Your mattress could be like silicon atoms, or a wiggling silicon atom, which is small, but it's not like electron size. And it's like a testament to how cool it is, how cool quantum field theory is, that we can use it for other things. Well, it's kind of a discrete field, right? Because you've got a spring and it's separated by material and they're all kind of vibrating and they follow like harmonic oscillator laws, and it's really good. In fact, field theory, quantum field theory, you should probably do that first and then.
You get undergrad and you go in there.
Well, springs, level 2 air trap experiment. Kind of like that, except you have infinitely many springs and are distributed in a plane. Or in 3 dimensions if you want. You know, cool. No, okay, no. Yes, so we've talked about some things. And it was lovely. And I will turn the lights back on now.
Thanks, Hadleigh.